Abalone age prediction is a crucial task in the seafood industry. Traditionally, the age of an abalone is determined by slicing its shell and counting the growth rates under a microscope. However, this process is labor-intensive and time-consuming. Machine learning offers an efficient alternative by predicting the age of abalone based on measurable physical attributes. So this approach can save time, reduce costs, and improve decision making for abalone farmers and seafood business. So after loading all of the libraries that we need for doing the machine learning, like running the regressions later, so we then take a look at the dataset. So the dataset contains various physical attributes of abalones, such as sex, length, diameter, height, whole weight, and so on. These features serve as independent variables for predicting abalone age. The target variable is the number of rings, which is used to estimate the age of an abalone using the formula age equals rings plus 1.5. So we then extract the features x and target variable y. X included numerical and categorical variables such as sex, length, diameter, height, whole weight, shaft weight, visceral weight, and shell weight. The target variable y was the number of rings, which is used to estimate the abalone's age. Before model training, several data validation steps were performed. Checking for missing values, um, ensure that all features were complete and did not require imputation. The number of unique values in each feature was examined to distinguish categorical from continuous variables, aiding in appropriate encoding decisions. Data frame information was reviewed to verify data types and detect inconsistencies. To understand the distribution of target variables, skewness was analyzed to determine whether transformations were needed. Additionally, outliers were identified using statistical methods such as Tukey Um, Tukiro, as extreme values could affect model accuracy. The data set was then split into the Tukiro is here, and this is the outliers. And then to understand, to improve the dataset was then split into training and testing sets to allow robust model evaluation while preventing overfitting. To improve model performance, feature standardization was applied. Mm, it's here. Given that attributes such as length, weight, and height exist on different scales, this score standardization was used to normalize the numerical variables. This ensured that no single feature dominated predictions due to differences in magnitude, leading to better model convergence and performance. The feature importance analysis is for the further highlighted which variables were most impactful in predicting abalone age. Using a random forest model, it was found that shell weight was the most influential feature, followed by visceral weight and shaft weight. Other weight-related attributes, such as whole weight, also played a significant role. On the other hand, features like length, um, diameter, and height had moderate importance, while the categorical variable sex was least impactful. This analysis aligns with biological expectations that heavier abalones tend to be older, emphasizing the relevance of weight-based attributes in age estimation. Hmm. As for the models, several regression models were tested to evaluate their effectiveness in predicting abalone age. Multiple linear regression was used as a baseline model, assuming a linear relationship between the independent variables and the target. It provided insights into how well a simple linear model could capture relationships between features. Lasso and ridge regression were employed to introduce regularization, preventing overfitting by penalizing large coefficients and reducing model complexity. Elastic Knight regression was also tested, combining the benefits of lasso and ridge by balancing feature selection with coefficient shrinkage. Beyond linear models, non-parametric and tree-based models were also explored. K-nearest neighbors KNN was applied to examine how well a distance-based model performed on this dataset, while support vector regression model um, abbreviated as SVR, was tested to determine if kernel-based transformations could improve accuracy. Decision tree regression was used to capture nonlinear relationships, but this model was prone to overfitting when trained on complex data. Random forest regression, an ensemble method that builds multiple decision trees and averages their predictions, was evaluated to improve robustness and reduce variance. So finally, a multi-layer perceptron, abbreviated as MLP, neural network was incorporated to test the effectiveness of deep learning approaches in predicting abalone age. This model was expected to capture complex patterns in the data but required careful hyperparameter tuning to avoid convergence issues. As for the results, among the models tested, um, multilinear regression and ridge regression both achieved R squared of 0.53 with MIC of 5.1 and MAE of 1.61. However, lasso regression underperformed with an R square of 0.14, suggesting that excessive regularization harmed predictive ability. Elastic net regression had a moderate R square of 0.38 but showed improvements over lasso. Nonlinear models performed better in certain cases. KNN achieved an R square of 0.5, outperforming lasso and elastic net, while SVR reached 0.41. Decision tree regression performed poorly with an R square of 0.2, indicating high overfitting. Multi-layer perceptron performed the worst with an R square of -0, failing to generalize effectively. So as for the insights and as for the key takeaways, the results indicate that ensemble models like random forests are likely the best fit for predicting abalone age due to their ability to handle complex relationships. Linear models struggled with underfitting, while deep learning approaches did not perform well, likely due to limited data complexity. Purple feature selection and scaling significantly impact model accuracy and efficiency. As for the industry impact, machine learning provides a cost-effective and efficient alternative to traditional age estimation methods in the seafood industry. Predictive models enable more sustainable harvesting decisions by ensuring abalones reach maturity before collection. The implementation of these models can improve productivity and profitability in abalone farming operations.